Hey there guys, it's Courtney here. We're just going to start on problem number 2 of the practice PQ. So it says, what causes the double bond rotational barrier in alkenes? So we're just going to put a pin in that question for a second because I want to just show something to you guys. We want to make sure first that we understand the hybridization of an alkene. So what hybridization is that it's determined by the groups that are attached to the carbons in this case. So each one of these carbons is going to have sp2 hybridization. And what that means is that each one has 3 different groups attached to it. So in an alkene, in this case, it's got sp2 hybridization. In an alkane, for example, we would see sp3 hybridization because it has 4 different groups attached to each carbon. In an sp hybridization, we would see in an alkyne, which has a triple bond. So each carbon involved in that triple bond is only going to have 2 groups attached to it, thus making it sp hybridization. Alright, so to jump back into the alkene molecule that we have in front of us here, is we see that it has the 3 hybridized sp2 orbitals coming off of the carbon. And this one in the center actually is making the sigma bond. I'll write that in pencil actually, so it's a little bit clearer. These 2 in the center are making the sigma bond in between those 2 carbons. The next thing we want to go over is that the hydrogens up on the side over here are making an S bond with each one of the carbons. So the carbon is putting out an sp2 hybridization towards the H, and the H is then giving back that S bond because it can only bond with one thing, so it only has an S bond, which is unique to the hydrogen in this case. We also have these P unhybridized orbitals right here. And what unhybridized means is that it is not attached to the carbon molecule. And instead, it experiences these 2 electrons out there in the center, which creates a bridge, if you will, in between the unhybridized p orbitals that are attached, not attached fully to each carbon. What the electrons do in this case is they prevent the p orbital from rotating around the carbon, or rotating around the center in this case. So the 2 electrons are so attached to each other that they prevent these p unhybridized orbitals from rotating. That overlap causes the rotational barrier in an alkene molecule that we see here. So if we go up to the question, we're determining what the cause is for the double bond rotational barrier in the alkene, which I just said would be D, the carbon P to carbon P overlap. So we can just go over the rest of the answers to just cross them out. So for E, right away, it says alkenes have no rotational barrier. That is not true because the P bonds create that rotational barrier. The P orbital itself keeps it from rotating. So because there are the 2 different bonds, it cannot spin. So I'm just going to cross that one out. We've also got, alright, let's look at C, which is the carbon sp overlap. We can cross that out because our carbons are experiencing sp2 hybridization, so they're not going to experience sp hybridization at all in this case. In an alkene, we would see that, of course, but in this case, definitely not. A we can cross out as well for similar to the same reason. A carbon with a sp3 hybridization we would see in an alkane, so not in this case when involving alkenes. And then B, this is carbon sp2 to carbon sp2 overlap. And this may end up tricking you guys, but I hope it doesn't, because we've got the two sp2 overlap taking place in the center, and that creates the sigma bond, as I said before. And the sigma bond is, also in a typical alkene and does not create a rotational barrier, because we see alkenes experience rotation. So the sigma bond is not preventing the rotation from occurring, so we can cross that one out. So our answer is D.